Math Review, Part 5, Vector Transformation. We're talking about how to use a matrix to transform a vector from one space into another. And I got to warn you, this is going to be a little bit heavier than the previous slides, so buckle up. So this is vector transformation. We just mean taking a vector and multiplying it times a matrix to get a new vector. So I'm calling the new vector v prime, the old vector v. So v prime equals v times m. A vector is actually just a matrix. It's a matrix with only one row. So this is a 1 by 3 matrix. And we can multiply that times a 3 by 3 matrix to get a new 1 by 3 vector. So just like with any other matrix, we go row by column and do a dot product. That's there. And then row by column again, and row by column again to get our 3 terms of the new vector. Now, I am writing out the vector as a row matrix. It's a row vector. And when you go online or you take other classes, you look in books, you've got about a 50-50 chance of whether you're going to see it with a row vector, or sometimes you're going to see a column vector. A column vector would go down instead. Now you can't multiply a column vector times a matrix in this order. The only way you can multiply them is in the other order. So you might see in a textbook or online, you might see v prime equals m times v. That would mean that they are using column vectors instead of row vectors. So in this class, I'm going to stick with the row vector for no particular reason other than that's what we did in 380, and I'm staying consistent with it. As I've said, in real game code, in game engines throughout the world, you've got literally a 50-50 chance of whether they use the row vector or the column vector. So there's not one way that is correct and one way that is wrong. You just go with the flow. It's the same thing. Keep in mind that it could go either way, but the math, remember, matrix multiplication is not commutative. So you get a different answer depending on which way you go, but you've got to be able to do the same transformation either way, right? So that means the transformation matrix here will have to look a little different depending on if you're using the row or the column. And it turns out it's just a transpose. It's just transposed, and we'll talk more about that again later. But you got to watch out for that. So if you're looking online, double check that they are using, that they're doing the row vector. And the best way to see it is to see, do they do vector times matrix, or do they do matrix times vector? If they do matrix times vector, then you know that all of the math they're showing you in that book is going to be the transposed matrix from our form. Okay, without further ado, let's do vector rotation. So a rotation matrix, I'm calling this m sub alpha. M sub alpha represents a rotation of an angle alpha around the z-axis in this case. So I've drawn it in 2D. So I've got my x and my y-axis here. That means the z-axis points up out towards us. So if I'm going to do a rotation of alpha, an angle alpha, I'm going to rotate from this vector. I'm going to take it around the z-axis in the positive direction. That's there. Now, if I'm using the right-hand rule, X is your index finger, curl it up towards Y, your thumb points out of the screen. Thumb's pointing out at the screen, and that means rotating around the thumb is the positive direction. So this is the new V prime that's going to result from this rotation. And here's the matrix that does that rotation. Now, I'm not actually deriving it here, I'm just giving it to you. I do have another video where I derive all of that. If you're curious, you can go looking into that. You don't have to derive it for this class. I will expect you to remember it. Now, You don't need to memorize this. I mean, you can, feel free if that's the way you like to roll, but I honestly, I cannot memorize it. The worst part about trying to remember these things is that if, as I said before, if you're in an engine that goes matrix times vector instead of vector times matrix, then this is the transpose, and that means the minus sign goes to the other spot. So it makes it really difficult to remember where that pesky minus sign goes. And it turns out remembering the minus sign is really the only part that's hard. So instead of trying to memorize it, I just do this. I just figure it out by doing a 90-degree rotation. And since I know what the 90-degree rotation is supposed to do, I can easily work out where these terms go. Let's do a demonstration. So we'll start with a very easy vector to begin with. The easiest vector you can possibly imagine is just the x vector, a unit in the x direction. Okay, so we'll start with that, and we're going to rotate it around our curious axis by exactly 90 degrees. So I'm going to rotate this x vector by 90 degrees around the z-axis, and that'll bring me to there, my x prime. And it's very easy to see in this diagram that x prime should be in the y direction. Okay, so how do I make a matrix that does that? So I'm just going to start with a guess. And it turns out I have a 50-50 shot. So I'm going to guess this one. Now, I'm deliberately choosing the wrong answer for this video so we can see how to see that it's wrong and how to fix it when it's wrong. So don't try to memorize this one. This is incorrect. This is just a guess. So how did I come up with this guess? First of all, I do remember that the cosine of the angle goes down the diagonal and the sine of the angle goes on the off diagonal. And the axis we're rotating around is still the identity matrix. That's still going to be one on that axis and zeros on the off diagonal for that axis. How do I know that? Picture a door. When you open and close a door, it rotates around its hinge. As it's rotating, the door handle is changing from being in the x direction to being in the y direction, or it's changing from being in the y direction to the x direction. But the hinges, they don't move because the hinges are on the axis of rotation. The axis of rotation is like the hinge. So that's the z-axis in this picture is the hinge, and nothing here changes. So that means I put the nothing changes part of the matrix there. Okay, and then I have cosines and sines in the other 4 spots. And I remember that there's one minus, and I have come to learn eventually that the cosines go here and the sines go here. If I get those wrong, I'm going to see that right here. So what I'm going to do is start with this guess, and I'm just going to try it out. I'm going to try to do this rotation with this guess. Let's do that. So fill in 90 degrees for our angle, and for our vector, I'm going to put in a unit in the x direction. So the cosine of 90 is 0, and the sine of 90 is 1. So I fill this matrix in, and here's a unit in the x direction as a vector. So if I multiply these out, what do I get? I get 1 times 0 plus 0 times 1 plus 0 times 0. That's 0. So I'll have a 0, and then a 1 times minus 1, 0, 0, 0, 0. So I'll have a minus 1, and then 1, 0, 0, 0, 0, 1. What I get is 0 minus 1, 0. And that is incorrect. I wanted 0, 1, 0. I wanted 0, 1, 0. I got 0 minus 1, 0. So I know I've got it wrong. And if you put your sines and cosines, if you mixed those up, you'll get it even more wrong. And that'll be pretty obvious once you do the multiply. So now that we know it's wrong, all we have to do is fix it. How do we fix it? Well, all that was wrong in our case was that we got 0 minus 1, 0 when we wanted a positive 1. So we have our sign wrong. The sign is wrong. How do we fix the sign? Well, the sign came from there. That's where that -1 came from, right there. So we're just going to take it and move it on. So let's do that. We'll fix the matrix and give it another go. Here's the fixed matrix, where I've put the -1 in the opposite side. By the way, this is the correct matrix now. Fill it in with the 90 degrees. Fill it in with the ones and -1s. And bang, zoom, Bob's your uncle. We got it right. So now we've verified this is the correct matrix to rotate around the z-axis. All right, so here they all are. Here are the 3 primary axes as rotation matrices. Here's the one we just did, rotation around the z-axis. And here's the rotation around the x-axis and rotation around the y-axis. So we'll see it again. The axis being rotated is always the identity matrix along that axis, both the row and the column. And so here's the y, and here's the z. And we always have cosine of alpha on the diagonal terms. So that's the cosine of alpha on the diagonal terms. We always have sine of alpha on the off diagonal terms. And one of those signs has a minus sign on it, but it's a little tricky because see how that minus sign sort of jumps back and forth. And like I said before, depending on if you're using row vectors or you're using column vectors, the minus sign will be in a different spot. So it makes it really hard to remember. For this class, if you're a memorize it type of person, I mean, feel free to just memorize these. We will need them for tests and stuff. So memorize them if that's the way you roll, but I definitely recommend trying it out with that 90-degree turn, even if you've memorized it. That way you can verify you got it right. All right, these 3 rotations around the primary axes, we call these the Euler angles. All right, what's the Euler angles? Euler angles just mean we rotate around the x-axis, we rotate around the y-axis, we rotate around the z-axis. And if you do those 3 in some order, you can get to any total rotation that you can imagine. You can get anywhere you want by doing some combination of x, y, and z rotations. Now, matrix multiplication is not commutative, as we've said, and that means that the order we do these, the order we combine these 3 matrices will give us a different answer depending on what order we use. And different engines do the rotations in different orders, and not every engine writer understood that there's a significance to this. It turns out, very unfortunately, many engine creators just see this as arbitrary. It's like, oh, the order is dependent, so as long as I specify what the order is, it doesn't matter. Well, it kind of does. They often will just say, well, I'll just use X, Y, Z. And depending on what the x-axis and the y-axis and the z-axis is for that engine, you can get just a weird combination. It turns out that there is one particular order that does make sense, and it's the one we use for aircraft. It's the one that makes sense, and that is to think of it, when you're thinking of it as a pilot, we do yaw, and then pitch, and then roll. So what does that mean? Yaw is a rotation around, in aircraft, that's the y-axis. That just means around the vertical axis. So a yaw is like to set a compass heading, like to face north, face east. That's what you do first. So if you think about it, if you're walking around, that's 99% of everything you ever do is how do I follow Google Maps? Well, I just do a whole bunch of what's called yaw. I do a whole bunch of different compass headings. Turn east, turn right, turn left. That's these. So we do that first. And then if for some reason we need to look up at something or look down at something, then we'll do our up down, the pitch elevation angle. And then finally, if for some reason you need to, you can do what's called a roll, which would be a rotation like to the side, where this is where you would like cock your head to the side. Not something you really do that often, unless you're flying in an aircraft. Okay, so that's why we do them in that order, because that's what makes sense to anyone who's grown up living here on Earth. You do most of your work in the yaw by setting your heading, and then maybe you look up and down, and then once in a blue moon you tilt to the side also. Okay, this is a little goofy. Thinking of it as we do this first, we do this second, we do this third can be confusing, because when we look at how we multiply them together, it may or may not be in that order, depending on, again, if we're doing row or columns. So it's very, very confusing. So that's a conversation you can get tripped up in very often. I'm going to run an example here where we are thinking in first person as if we are the pilot. So if you're the pilot of a plane, you first yaw, then pitch, then roll.
All right, let's take a little look at Euler angles using, as an example, this little, hold on, this little Unity scene. I got my little airplane in there. Okay, so the rotation of the airplane is connected to the plane itself, to the pilot on board. So what we do first is we would yaw. This is yaw. So let's head east. So boom, we turn head east, and now pitch up, like we're gonna climb. Okay, and then finally we roll. So that's how we do it. We do it in that order, and that's why that order makes sense.
So that's rotation matrices, Euler angles. Let's talk about scale now. Something else you can do with vectors is you can scale them, of course. So here is an original vector v, and then we've scaled it up by multiplying it by some scalar s. So we got v prime equals s times v. And as a matrix, we can write that like so. You just put the scale along the diagonal, and you multiply that out, and you just get SV. We can put different scale values. Since this is in a matrix form, this turns out to be 3 entries in the matrix. We don't have to put the same value in all 3. So if you want, you could scale something in the x direction, something in the y direction, something else in the z direction. And that's something that we sometimes allow, sometimes we don't allow. Okay, there's 2 kinds of vectors in the world. There are position vectors and direction vectors. We've talked about this a bit before, so this should be some review, but it bears reviewing. Let's take our little pirate ship and let's put a point right on the nose of the ship. So this point V, and that'll be our position vector. This is the position of the front of the ship. Now let's take a direction vector. Call this one F. This is the forward vector. That's the way the ship is pointing. So what happens when we transform these vectors? So the first transform we talked about, let's do a rotation. I'm going to show a 90-degree rotation here. I've rotated my pirate ship. So where is that point V? Here's the new point V. The old point V, when it goes through this 90-degree rotation, ends up here. So positions rotate. Cool. How about directions? We had the forward vector was pointing this way, and now we apply this rotation, and the new forward vector points that way. And so directions also rotate. No surprise there. Okay, how about what if we translate the ship? Let's translate the ship. I'm going to push it down like this to here. So we've got our position V on the nose of the ship. It has translated down. Positions translate. How about our forward vector? This one's a little tricky because the forward vector, I've drawn it down here, but which way does it point? It still points straight down the x-axis because direction vectors do not translate. Direction vectors rotate, but they don't translate. That's the difference between direction vectors and position vectors. Now that makes them a little bit different, and that means we have to treat them differently in the math. How do we handle that? Here's how we handle it. We're going to go to a fourth dimension. We're going to add a fourth dimension. We've got our x, y, and our z. We need a new fourth dimension. And what comes after z? Well, of course, w comes after z, right? Okay, so we'll use x, y, and z means just what it used to mean. The w is going to mean something new. And to see what's new, let's give ourselves a 4x4 matrix. And I'm sort of just cutting to the chase here. I'm not explaining why yet, but as we do this multiplication, we'll see why, I think. I took my original 3x3 matrix we had from the previous slide. So that's like, maybe that's a rotation or a scale, or it's a rotation and a scale. That goes here in the 3x3. On the bottom, I'm putting the translation. And I've put zeros here and a 1 here. Let's do the multiplication and see what we get. When I multiply the x, I take this, the whole vector, and dot it with this first column, and I get what I had before. This is exactly what I had before, and then this new term comes on the end. And the same thing happens for the y-axis. Same thing happens for the z-axis. Now let's take a look at this new thing that got added. It's always VW times the translation in that axis. And what we see is that if we wanted to translate this vector, we wanted to just translate it, all we have to do is add. All I have to do is add a position. So if we want to add tx, ty, tz to the vector, the way to do that is to make VW equal 1. And then if VW equals 1, then we'll just say, give me the translated vector, or give me the transformed vector, the rotated vector, and just translate it by this amount. Okay, so now we know if we want to include translation, we'll put it in the bottom of the matrix, and we'll put a 1 in the VW. Okay, but what about a direction vector? For a direction vector, we did not want to use the translation. We could accomplish that by simply not including it, by just making it a 3x3, and then it won't include it. But another trick we can do is just put a 0 for the W, and then we'll get a 0 times each of those in the new direction vector. The direction vector will rotate, it'll scale, but it'll just ignore the translation. Okay? All right. This is going to keep coming up over and over, and people forget it over and over. So I'd like to stress it again. If you see a 1 here, this is a position vector. If you see a 0 here, this is a direction vector. If you're trying to transform all the vertices of a geometry, those are positions. The vertices are at a particular position. So the vertices need a 1 on here when they multiply by this matrix. The normals of a vector, the normals of a geometry, they are directions. They say which way does this thing point. They don't have any translation, and therefore for normals, we're going to put a 0. Okay. Finally, let's combine these things together. Combining them together, we had our rotation matrix, we had our scale matrix, and now we have our translation matrix. They go in this order. Because we're using row vectors, the vector goes in the front. And so we scale it, we rotate it, we translate it in that order. Okay. Because matrix multiplication is associative, I can drop parentheses around here, which means I could scale the vector, get a new vector, and then I could rotate that new vector to get a new vector, and then I can translate that new vector to get a new vector. Or another way to do this is I can multiply these matrices together to get a new matrix, multiply those matrices together to get a new matrix, And then now that I've got a single matrix here, which I'm calling the SRT matrix, I can multiply that matrix times the vector to get my new vector. I can combine all three transformations into a single transformation matrix. So I can combine scale, rotation, and translation together, as long as I put them in that order. Okay, let's show what goes wrong if we botch the order. So let's make a little question out of that. What if I have a matrix to scale by 10 times and a separate matrix to translate by 10, 20, 30? If I combine them as translation times scale, and then I apply that to a vector, what's going to happen? Is that going to work? And let's try it also with scale times translate and see which one is correct. So on the next slide, I'm going to do that. You want to work it out yourself, pause it, and then come back when you've got it. So here we go. I'm going to do it. Let's make our T matrix. Here is the translation matrix for 10, 20, 30. All you do is put your translation across the bottom. The rest of the matrix is an identity. Okay, here's your scale matrix. I want to translate by 10, a uniform scale, or 10 on, it says 10x, it means 10 times. So 10, 10, 10. Okay, those are my two matrices. Let's combine them as TS. So we'll just take T and multiply by S, and that's just here. All right, now let's transform a point using this new matrix. What point? I don't know, the easiest point is 0. Let me just translate 0, 0, 0 with a 1, because this is a position. We'll take the 0, 0, 0 vector, and first, before we do it, so it's over here, but before I even do it, where should the 0, 0, 0 point go if I have scaled it by 10 and translated it by 10, 20, 30? Well, scaling 0 does nothing, so I should then just add 10, 20, 30. I should get 10, 20, 30. Let's multiply times this TS matrix that we've got and see how it turns out. I've got that matrix multiplied times that. I get 100, 200, 300, which is incorrect. I wanted 10, 20, 30. I got 100, 200, 300. Why did I get that? Because I didn't do scale and then translate. I did translate and then scale. I translated it to 10, 20, 30, and then I scaled it to 10 times that. Okay, so instead, let's try the ST matrix. If I multiply those matrices in that order, this is what I get. And when I multiply it out, I get the correct answer. Yeah, that's right. Okay, so ST is the way to do it. And another way you can tell really easily right away just by looking at the matrix. I have the scale down the diagonal, and I have the translation along the bottom. And this is something a little bit magical that I really want you to see and look at. I can look at this matrix right here, and just purely by eyeball, I can tell you that the translation of this matrix is 10, 20, 30, and the scale of this matrix is 10, just by looking. If I see this matrix in the debugger somewhere and I don't know where it came from, I can tell you what it is. I can tell you that's a 10 scale and it's a 10, 20, 30 translation, and there's no rotation. I can tell just by looking.